Welcome! In this session, we will explore an interesting coding problem, logical OR of two binary grids represented as quad trees. We'll break down the problem step by step, discuss approaches, and work toward an efficient solution. Let's dive in. In this problem, we are working with a data structure called a quad tree, which is used to represent binary grids. A quad tree is a hierarchical structure where each internal node has exactly 4 children. Each node corresponds to a specific region in the grid, and this division continues recursively until we reach regions with uniform values, either all zeros or all ones. These uniform regions are represented by leaf nodes. The objective here is to compute the logical OR of two such binary grids. The logical OR operation is applied cell by cell. For example, if a cell in the first grid has a value of 0 and the corresponding cell in the second grid has a value of 1, then the result for that cell is 1. Similarly, if both cells are 1, the result remains 1. The final output should be a new quad tree that represents the logical OR of the two given input quad trees. The output of this problem is the root of a new quad tree that represents the logical OR of the two input quad trees. Let's look at a few examples to understand this better. In the first example, both quad tree 1 and quad tree 2 are leaf nodes with a value of 0. This means that both grids are entirely filled with zeros. Since the logical OR of two zeros is 0, the resulting quad tree is also a leaf node with a value of 0. This represents a binary grid that is still completely filled with zeros. In the second example, both quad tree 1 and quad tree 2 are leaf nodes with a value of 1. Here, both grids are completely filled with ones. The logical OR of two ones is 1, so the resulting quad tree is a leaf node with a value of 1. This indicates that the resulting grid is entirely filled with ones. In the third example, things become more interesting. Both quad trees are non-leaf nodes and represent grids divided into subregions. Each subregion is recursively represented as a child node, either a leaf or another internal node. The task is to compute the logical OR at each corresponding child node level. For the third example, the output quad tree captures the result of the logical OR operation applied at each corresponding child node. The top left child nodes in the input grids have values 1 and 0, so their OR is 1. Similarly, the top right child nodes both have a value of 1, so their OR is also 1. The bottom left child nodes have values 0 and 1, resulting in an OR of 1, while the bottom right child nodes both have values of 0, making their OR 0. This gives us a new quad tree where the children represent these resulting values. The final output is a quad tree with these computed values in the respective quadrants. To summarize, a quad tree node is considered a leaf node if its isLeaf attribute is true. Leaf nodes represent uniform subregions of the grid. If a node is not a leaf, it must have exactly 4 children, each representing a distinct, non-overlapping subregion of the grid. These constraints ensure that the quad tree accurately and efficiently represents binary grids of size 2 to the power of n x 2 to the power of n, with n ranging from 0 to 10. This structure enables us to perform operations like the logical OR in a recursive and hierarchical manner, making it well suited for problems involving binary grids. To solve this problem, one possible approach is the brute force method, which involves directly converting the quad trees into their full binary grid representations. Once we have the expanded grids, we can perform a logical OR operation cell by cell across them, and finally convert the resulting grid back into a new quad tree. While this approach is conceptually simple and easy to implement, it comes with significant inefficiencies. The main issue lies in the fact that quad trees are designed to be space efficient, especially for sparse grids. Converting them into full grids eliminates this efficiency, leading to high memory usage. For a quad tree of depth d, the full grid size can be as large as 2 raised to the power of depth squared. This means the space and time complexity can become n squared for dense grids, where n represents the grid size. While straightforward, this approach is not feasible for deep or sparse quad trees due to its high space requirements. A more efficient method is to leverage the recursive structure of quad trees, using a divide and conquer approach to compute the logical OR directly on the trees. Since quad trees inherently represent regions of the grid, we can recursively calculate the OR operation at the node level instead of expanding the grids. The result at each node depends on the values of the corresponding nodes in the two trees. If either node is a leaf with a value of 1, the result is a leaf node with value 1. If one node is a leaf with a value of 0, we simply return the other node. When both nodes are internal nodes, we recursively compute the OR for each of their corresponding children. This method avoids the inefficiencies of grid expansion, preserving the space advantages of quad trees. The time complexity is guided by the number of nodes across the two trees, making it more efficient, especially for sparse grids. However, this approach requires careful handling of edge cases, such as when one node is a leaf and the other is not. For this problem, we chose the recursive logical OR approach due to its balance of efficiency and alignment with the natural structure of quad trees. This strategy avoids the overhead of grid expansion and leverages the hierarchical properties of the trees. The process is straightforward. If either node is a leaf, we return a leaf node with value 1 if either one has a value of 1. Otherwise, we return the other node. If both nodes are internal, we recursively compute the OR operation on their children. After processing the children, if all 4 resulting children are leaf nodes and share the same value, we merge them into a single leaf node to maintain compactness. This method is not only clean and intuitive but also ensures optimal time complexity of O(m), where m is the total number of nodes in the two trees being processed. The space complexity of this recursive approach is O(h), where h represents the maximum depth of the quad trees. This is because the recursion stack only needs to hold calls up to the depth of the tree. By avoiding full grid expansion, the approach minimizes memory usage and makes the solution well suited for sparse or deeply nested quad trees. Overall, this strategy effectively balances clarity and performance while fully utilizing the properties of quad trees. Compared to the brute force method, it avoids unnecessary computational overhead and memory consumption, making it the optimal solution for this problem. To start, the problem involves working with quad trees, a hierarchical data structure used to represent 2D binary matrices in a compressed format. Each node in a quad tree can either be a leaf node or an internal node. Leaf nodes represent regions where all values are uniform, either all zeros or all ones. On the other hand, internal nodes represent regions that are subdivided into 4 quadrants: top left, top right, and bottom right. By using this structure, quad trees provide an efficient way to store sparse or uniform binary grids. Our goal in this problem is to take 2 quad trees, convert them into their corresponding binary grid representations, perform a logical OR operation on the grids, and then convert the resulting grid back into a quad tree. This approach allows us to manipulate the data efficiently while leveraging the strengths of both quad trees and binary grids. The next step is to convert the 2 input quad trees into their full binary grid representations. Since quad trees represent 2 to the power of n x 2 to the power of n grids, the first task is to determine the size of the grid by extracting the height of the tree. Once we know the grid dimensions, we can use a recursive function to traverse the quad tree. If the current node is a leaf, we fill the corresponding region in the grid with the leaf's value, such as all zeros or all ones. If the node is an internal node, we recursively process its 4 children, ensuring each child corresponds to its appropriate quadrant boundaries. To facilitate this, we first initialize an empty grid of size 2 to the power of n x 2 to the power of n and populate it during the recursive traversal. The output of this step is 2 binary grids, one for each input quad tree, which can then be used in the logical OR operation. Once we have the resulting binary grid after performing the logical OR operation, the next task is to convert this grid back into a quad tree. This involves recursively checking each region of the grid to determine whether it is uniform. If a region contains all zeros or all ones, we create a leaf node to represent that region. If the region is not uniform, we subdivide it into 4 quadrants and recursively process each quadrant to create child nodes. The process continues until the entire grid is represented as a quad tree. The final output of this step is the root node of the newly constructed quad tree, which encapsulates the result of the logical OR operation in a compressed hierarchical format. There are several key insights to keep in mind when working with this algorithm. First, quad trees are particularly space efficient for sparse or uniform binary grids, and the algorithm takes advantage of this by converting the compressed quad tree form into a full grid only when necessary for computation. Second, the recursive nature of the quad tree structure is central to both traversal and construction, as each node inherently divides the grid into smaller subregions. Third, the logical or operation itself is efficient, as it involves a straightforward cell-by-cell comparison, which operates in n squared time for a grid of size 2 to the power of n x 2 to the power of n. Additionally, the algorithm is designed to handle edge cases, such as fully uniform grids, where the quad tree consists of a single leaf node, and highly subdivided grids, ensuring that all regions are processed recursively. The combination of quad-tree nodes and binary grids as data structures provides a balance between compression and computational simplicity. Finally, let's analyze the complexity of the algorithm. The conversion from a quad-tree to a binary grid has a time complexity of n squared, where n represents the size of the grid, and a space complexity of n squared, due to the storage of the grid itself. The logical OR operation, which involves a cell-by-cell traversal of the grids, also has a time complexity of n squared, and a space complexity of n squared, for the resulting grid. Converting the binary grid back into a quad tree similarly operates in n squared time, with an additional n squared space complexity for the recursive stack during construction. Overall, the algorithm's complexity is dominated by the grid operations, resulting in an n squared time complexity for the entire process. This balance of time and space efficiency leverages the strengths of both data structures to achieve a practical solution. This Python solution solves LeetCode problem number 558, logical OR of two binary grids represented as quad trees. The problem requires combining two quad trees using the logical OR operation. The solution starts by defining the node class to represent each node of the quad tree. Each node has attributes for its value, val, whether it's a leaf node, isLeaf, and pointers to its four child nodes, top left, top right, bottom left, bottom right. The main logic is implemented in the intersect method of the solution class. This method takes two quad trees, quad tree 1 and quad tree 2, as input and returns a new quad tree representing their logical OR. #### key steps. 1. Base case for leaf nodes. If quad tree 1 is a leaf, it is returned directly if its value is true, logical 1. Otherwise, quad tree 2 is returned. Similarly, if quad tree 2 is a leaf, it is returned directly if its value is true. 2. Recursive OR on child nodes. If both trees are non-leaf nodes, the method recursively applies the intersect function to their corresponding child nodes, top left, top right, bottom right. 3. Merging results. After computing the logical OR for all child nodes, the algorithm checks if all four resulting child nodes are leaf nodes with the same value. If they are, these nodes can be merged into a single leaf node. Otherwise, a parent node is created with the combined children. This approach ensures the quad tree representation is optimized, merging regions when possible to reduce the tree's complexity. ### complexity. Time complexity. The function traverses the nodes of the two input trees. For quad trees with n nodes, the complexity is n. Space complexity. The recursion stack requires h space, where h is the height of the trees. This complete implementation handles all edge cases, including trees with mixed leaf and non-leaf nodes, as well as uniform grids represented by single leaf nodes. Here, we start with the definition of the node class, which represents a node in the quad tree. Each node has two main attributes, val, which is a boolean indicating the value stored in the node, and isLeaf, which tells us whether this node is a leaf node or an internal node. If it's a leaf node, it will not have any child nodes. For internal nodes, we define four child pointers, top left, top right, and bottom right, representing the four quadrants of the grid. The class includes multiple constructors to allow flexibility in initializing nodes. For instance, you can create an empty node, a node with just a value and leaf status, or a fully initialized node with all child nodes specified. This structure is the foundation for manipulating quad trees in our solution. The intersect method is where the logical OR operation between two quad trees is implemented. We first handle the case where the first tree is a leaf node. If its value is true, it overrides the second tree, as true or anything is always true. Otherwise, we return the second tree. Similarly, if the second tree is a leaf, we prioritize it if its value is true. Next, we handle the case where both trees are internal nodes. We recursively apply the intersect method to each of their corresponding quadrants, top left, top right, and bottom right. After merging the quadrants, we check if all four resulting children are leaves and have the same value. If so, we simplify them into a single leaf node to optimize the tree structure. Otherwise, we return a new parent node with the merged children as its quadrants. This ensures the resulting tree correctly represents the logical OR of the input trees. In this example, we're working with two quad trees that are both leaves. The first tree, quad tree 1, has a value of 1 and is a leaf, while the second tree, quad tree 2, has a value of 0 and is also a leaf. Since quad tree 1 is a leaf, we check its value. If the value of a leaf node is 1, it will dominate the logical OR operation, and we can directly return that node. Here, quad tree 1 has a value of 1, so the result of the logical OR is simply quad tree 1 itself, which is node, val equals 1, is leaf equals true. This is the final output for this case. Now, let's look at a more complex case where both quad trees have a mix of branches and leaves. The input consists of two quad trees, both non-leaf nodes. Quad tree 1 has children where the top left and top right are leaves with the value 1, and the bottom left and bottom right are leaves with the value 0. Similarly, quad tree 2 is also a non-leaf node, but its children have a different configuration. The top left is 0, the top right is 1, the bottom left is 1, and the bottom right is 0. Since neither tree is a leaf, we need to recursively compute the logical OR for each corresponding quadrant of the trees. The recursive logical OR begins with each pair of corresponding child nodes. For the top left quadrant, we compute the logical OR of node 1, true, and node 0, true. Since the first node is a leaf with a value of 1, we return it directly. For the top right quadrant, both nodes are leaves with the value 1, so the result is simply node 1, true. In the bottom left quadrant, node 0, true, is ORed with node 1, true. Here, the second node dominates because it has a value of 1, so we return node 1, true. Finally, for the bottom right quadrant, both nodes are leaves with the value 0, so the result is node 0, true. After processing all quadrants, we check if the results can be merged into a single leaf. The results are node 1, true, node 1, true, node 1, true, and node 0, true. Since not all values are identical, we return a new internal node with these quadrants as its children. The final output for this example is a non-leaf node. This internal node has the following quadrants: top left is node 1 is leaf equals true, top right is node 1 is leaf equals true, bottom left is node 1 is leaf equals true, and bottom right is node 0 is leaf equals true. This structure represents the logical OR result of the two given quad trees. Now, let's explore another scenario where one tree is a fully expanded leaf and the other is a non-leaf tree. In this case, quad tree 1 is a single leaf node with a value of 1, while quad tree 2 is a non-leaf node with all of its children being leaves, each with a value of 0. Since quad tree 1 is a leaf, we immediately check its value. If it's 1, it dominates the logical OR operation, and we can directly return quad tree 1 as the result without needing to process quad tree 2. Here, quad tree 1.val is indeed 1, so the logical OR result is simply node val equals 1 is leaf equals true. This is the final output for this example. When analyzing the time complexity of the intersect function, it's important to account for the recursive nature of quad trees. A quad tree is a hierarchical structure where each node divides a 2D grid into 4 quadrants, represented by its children: top left, top right, bottom left, and bottom right. To measure complexity, we define D as the maximum depth of the tree and N as the total number of nodes. In the best case, if one or both input trees are leaf nodes, the function resolves in constant time, O1, since no recursion is required. However, in the worst case, when both trees are fully expanded, the algorithm visits each node once and performs recursive calls for all nodes, resulting in a time complexity proportional to the number of nodes, which is O(n). Now, let's break down the recursive calls. For each non-leaf node, the algorithm makes 4 recursive calls, one for each child node: top left, top right, bottom left, and bottom right. However, recursion terminates as soon as a leaf node is encountered, ensuring that nodes are never revisited. Despite the 4 calls per level, the total number of recursive calls is tightly bound to the number of nodes in the quad tree. This gives us an overall time complexity of O1 in the best case when processing leaf nodes, O(n) in the worst case when every node is processed, and O(n) on average, depending on how the input trees are structured. Next, let's consider the space complexity of the intersect function. This is influenced by two main factors: the recursive call stack and the creation of new nodes. The depth of the recursive call stack is determined by the depth of the quad tree, which is O, D. If the tree is fully expanded, this depth relates to the total number of nodes, as D equals log n. Additionally, in the worst case, the function may create up to O, n, new nodes when merging non-leaf nodes, leading to a space requirement proportional to the size of the resulting tree. Combining both factors, the overall space complexity is O(1) in the best case when recursion is minimal and no new nodes are created, and O(n) in both the worst and average cases, depending on the structure of the input trees. Lastly, let's compare this quad tree approach to a brute force method. In a brute force solution, you would compute the logical OR for each individual cell in the original 2D grids. If the grids have dimensions 2D x 2D, the total number of cells is 4D, resulting in a time complexity of O(4 to the power of D). The quad tree approach, however, avoids processing every single cell by leveraging its hierarchical structure. Instead of 4D operations, the algorithm processes only the n nodes in the quad tree, significantly reducing the complexity to O(n). To illustrate, a fully expanded quad tree of depth D has about O(4 to the power of D) nodes, but uniform regions of the grid allow for large leaf nodes, reducing n. The intersect function processes each node once, ensuring time complexity remains O(n). Space complexity, including the recursive stack and new nodes, is similarly bounded by O(n). This makes the quad tree method exponentially more efficient than brute force for large grids, especially when uniform areas are present. When working with quad trees, there are several common mistakes to avoid. One frequent issue is incorrectly converting quad trees into grids. Since quad trees represent hierarchical divisions of space, failing to account for their nested structure can lead to inaccurate grid representations. For example, if you skip over a child node or fail to properly divide regions, your grid won't reflect the true data. Another mistake is inefficient handling of large grids. Expanding a quad tree into a full binary grid, especially for large dimensions like 1024 by 1024, can consume significant memory and computational resources, which is often unnecessary. Lastly, mishandling edge cases is a critical pitfall. For instance, when one quad tree is completely null or entirely filled, logical operations like OR AND can often be simplified without complex traversal. Overlooking these shortcuts can increase computation time unnecessarily. Another mistake to look out for is overcomplicating the merging logic. When merging two quad trees, some people write overly complex recursive functions, which can lead to bugs and make debugging difficult. A better approach is to ensure that recursion is systematic, handling each node in a straightforward and consistent way. Additionally, ignoring asymmetry in tree depths is a common oversight. Quad trees can have different levels of detail, and assuming they are always balanced or have similar depths can cause problems. For instance, if one tree represents space at a finer granularity than the other, you need to account for this disparity during the merging process, ensuring that the finer details are correctly integrated. Now, let's consider some insights that can elevate your performance in an interview setting. First, understanding the patterns in quad tree problems is crucial. These questions often involve recursion and tree traversal, so emphasizing your ability to apply divide and conquer techniques is important. Next, focus on optimization. Be prepared to discuss the trade-offs between converting quad trees to grids versus working with the trees directly. Highlighting memory efficiency can leave a strong impression. Also, anticipate edge cases, such as merging a fully filled tree with an empty one or handling trees with imbalanced depths. Finally, communicate clearly. Explain how recursion mirrors the hierarchical structure of quad trees, as being able to articulate this relationship demonstrates a deep understanding of the problem. To further enhance your understanding, it's helpful to explore related problems. For example, LeetCode problem 427 focuses on constructing a quad tree from a binary grid, while problem 558, which we're discussing, deals with logical operations between quad trees. Additionally, problems 116 and 114 involve tree traversal and flattening hierarchical structures, which share conceptual similarities. Beyond these problems, there are alternative approaches to consider. One option is a recursive direct merge, where you handle quad tree nodes without converting them to grids. This saves memory but requires careful handling of recursion and node types. Another option is a hybrid approach, using grid conversion for smaller quadtrees and recursive merging for larger ones. This balances simplicity and efficiency, but deciding when to switch approaches adds some complexity. Finally, an iterative traversal approach can be an alternative to recursion. By using stacks or queues, you can simulate the recursive process iteratively. This method avoids stack overflow issues, which can be a concern with deep recursion. However, while it's more robust in terms of memory management, it may be less intuitive to implement, as you'll need to manage the traversal explicitly. This approach is worth considering in scenarios where recursion depth could become problematic or when you want more control over the traversal process. Great job! To recap, we tackled the problem of logical or with quad trees, explored an approach, and discussed key insights. Remember to practice and refine your skills, and I hope you found this helpful. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!